Hello students, last time we were talking about what they call it, certain effects in organic chemistry, inductive effect, electromagnetic effect, resonance or mesomeric effect. In inductive effect we have seen that is permanent effect and electromagnetic effect was found to be temporary one. For example here in the case of alkene, when we are having alkene, so their Morkovnikov rule is example of electrophilic addition, and here it is the application of inductive effect because the product formed will be guided by which carbocation is stabler, and the stability of carbocation is given by inductive effect. Similarly, if you can take this, the case of this is application again of inductor plus psi effect. In this case, if you add water in the presence of dilute sulfuric acid and mercuric sulfate, the product formed is this, not this. This is not formed because this will be involving the formation of primary carbanion. This is nucleophilic addition. So why this is formed? Because primary, the order of stability of carbanion is greater than primary greater than secondary greater than tertiary. So that's the reason here out of the two, out of secondary and primary, which is formed? Primary is formed. So why it is so? Because it is more stable, because R has got plus I effect as we have seen in the last video. This is example of nucleophilic addition. When we are talking about property of alkene, propene plus HBr, that was electrophilic addition as we have seen in last video. So there secondary carbocation formation was preferred to the formation of primary carbocation. Let us continue with whatever we were doing, that is resonance. We were doing about resonance. To resonance we have seen when a compound can be assigned to a more electronic structures, none of which is capable of explaining all its known properties, and actual structure is said to be lying in between those structures. We have seen the example of carbon dioxide, and it was seen that the carbon dioxide is there. So naturally, this is the carbon dioxide. Here you are having three structures. So that is, how does it prove that these all contributing? When you are seeing the bond length between carbon and oxygen is neither corresponding to single bond, nor to double bond, nor to what they call it, triple bond. So as a result of that, this is the example of resonance. Let us continue with this. Conditions for the rules for writing, resonating, contributing, or canonical structures. What are the rules for writing, resonance? What are the rules for writing resonating structures, contributing structures, or canonical structures? So first of all, the relative arrangement of nucleus should be remaining same. The relative arrangement of nucleus should be always same. the relative arrangement of nuclei should be same in all structures. In all structures. For example, you are having benzene. We have just seen the case of carbon dioxide. Carbon is always present in the center. In all these structures, carbon is present in the center and oxygens are present along the sides. So it is not like this in some structure you will be having oxygen as a central atom. That is wrong structure. So this is the first condition. Second condition is that the number of unpaired electron in all should be same. Number of unpaired electron in all resonant structures should be same. The number of unpaired electrons should be same. For example, you are having this. So these two are resonating structures. Allylic free radical. So here number of unpaired electron in both structures is same. Number of paired or unpaired electrons should be always same. Then the third thing is that what we should be having, the relative arrangement we have seen should be same. For example, here you can take more examples from this. So that we'll be asking in the questions later on. So here octet rule should be observed. Octet rule should be observed. Octet rule should be observed. For example, you are having this. CH2, then this. So here this structure is wrong. Why this is wrong? Because in this case nitrogen is surrounded by 10 electrons. So this octet rule is not observed. So nitrogen cannot be surrounded by 10 electrons. Why it is so? Because the second row elements, the second row or second period elements not having D subshell. Second period elements. Nitrogen belongs to second period, starting with lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. All of them are second period elements not having D subshell. So as a result of that, it is not possible for them to accommodate more than 8 electrons. For example, nitrogen cannot do so, but phosphorus can do so. But phosphorus is having D subshell. This is D orbital. So as a result of that, that is responsible for anomalous behavior. This is responsible for anomalous behavior. This is very important thing in inorganic chemistry. The second period elements are behaving in an anomalous manner. The nitrogen is behaving differently than the remaining other elements of the group, 15th group, phosphorus, arsenic, antimony, bismuth. So nitrogen is something belonging to second period. It is not having D subshell, so it cannot accommodate the 10 electrons. So this structure is wrong because it is violating the octet rule. Octet rule is not observed. So here it is absorbed. So naturally, one should be always aware of the things. Then next thing is that, okay, let us see the more examples. What are the contributions? How does which structure will be contributing more and this? For example, continuing here, relative arrangement of nucleus should be same. We have given the example of carbon dioxide. Suppose you are having this. These are not referred as resonative structures. Not resonative structures. Why it is so? Because the relative arrangement of nucleus is not same. The relative, these are tautomers. These are tautomers. Acetaldehyde, this is acetaldehyde, this is the vinyl alcohol, this is ethanol, this is ethanol, it is what they call it ethanol. So this is something not resonative, these are not resonative structures, these are tautomers. Tautomer means the functional isomer in equilibrium. Functional isomer in equilibrium. Why functional isomer? Because molecular formula is same. The difference is in their functional group. Here functional group is CHO, their functional group is OH. So naturally these are not isomers, these are not resonative structure, these are isomers. Similarly, if you are having this structure, H3PO3 and this, these are not resonative structures, right? Here just see relative arrangement of nucleus is different, so not resonating structure. So one should know what are the conditions for writing resonating structures. Then the next thing is that, okay, which structure is more important while writing the resonating structures? Which is having less charge separation. Charge separation. Structure make lesser contribution. Or it is unstable. It is unstable. Charge separation will be making the structure unstable. For example, you are having this. Here positive and negative charges are there. But if you see the structure of this phenate ion, this is contributing this. So this structure is more stable as compared to this, because in this case charge separation, so therefore phenol acts as acid, because this is second is more stabilized by resonance than first, because in first we are having charge separation. So when phenol is acting as acid, why it is so? Because phenate ion is more stable, it is more stabilized by resonance than phenol. Both of them are having plus resonance effect, this OH group, as well as O minus group. These are having plus resonance effect and plus mesomeric effect because donation of electron is taking place. But here this is making it more stable while as compared to this. So that's why phenol will be having tendency to form phenate ion. So phenol is acting as acid and phenol is better than alcohol. Better than this. It is better than this. So phenol is better than this, or you can say it is better than cyclohexanol. Why it is better? Because here you can have resonance effect, here resonance effect is not possible. So charge separation. Then we are having this. The charges should not be on the adjacent atom. The like charges should not be on neighboring atoms. For example, you are having this structure versus this structure. This is not stable because here charge separation, the charges are present, like charges are present on neighboring atom. So this will be making the structure unstable. So this structure is quite unstable. So this is quite unstable. For example, you are having one more rule, say, this is say, you are having this. So this is more stable, then this is more stable, this is least stable. Because positive charge is present on electronegative atom. So we have to observe certain rules by writing resonative structures, and that will be only possible if you are knowing the effects. So this was something from resonance, writing the resonative structures. Now here we have come to know that OH and phenate ion are electron donating group. Electron donating group. So as a result of that, what should be there when you are having electron donating group? So that will be affecting the things. Just see, here we have got, it is explaining the acidity. Acidity means tendency to lose proton. So phenol is having tendency to lose proton because it will be resulting into formation of phenate ion, which is more stabilized by the resonance. So here it has explained the acidity of phenol, better acidity of phenol than aliphatic alcohol or alicyclic compound. Then continuing in the same fashion, it means that if it is having electron releasing effect, certain groups should be having electron withdrawing effect also. Let us see that and how it is affecting the things. So let us continue in that direction. So we have got two types of groups. One is having plus R or plus M effect. For example, we have got OH group, NH2 group, and or halogens. Just see, halogen was having minus I effect. Halogen. It will be known as halo. Halo group. It is hydroxyl group, amino group, alkoxy group. So these are having, similarly you can also have this SH or SR. So here all of them are having this electron releasing group effect. All of them are having electron releasing effect. And then minus R, electron releasing. Electron withdrawing. Here you are having NO2. Then you are having CHO. We are having CNN. CN group. Then you are having sulfonic group. Then you have got this group. Or so this is known as sulfonic group. Just see SH is having electron releasing effect, SO2, OH is having electron withdrawing effect. Why it is so? Because if you see the structure, so here lone pair is not present, that is busy in making coordinate bond with oxygen. So this is the difference. NH2 was having lone pair, so it is electron releasing. NO2 is having electron withdrawing. Why we have seen it in inductor effect also. So here nitrogen is electron deficient. So these groups are having what they call it electron withdrawing resonance effect. So just see, this was same in the inductor effect. But here it is different. Here it is different. For example, when you are having this CH3, CH2, this is say X plus KOH. In this case, CH3, CH2, OH minus KX. This is nucleophilic substitution. Here it is reacting faster. Then vinyl halide. It will be reacting with this very slowly react. Why it is so? Because of this resonating structure. So here you are having this resonating structure. So double bond is there. So double bond will be making it stronger bond. So naturally it will be difficult to break that. So that explains why vinyl halide is having something lesser reactivity, low. It is reacting at a slower rate as compared to aliphatic alkyl halide, so which is ethyl chloride. Similarly, you can say this will be reacting faster. This is chlorobenzene. Benzyl chloride is reacting faster than chlorobenzene, or cyclohexyl benzene will be reacting faster than chlorobenzene towards nucleophilic substitution reaction. So that is some of the applications of this mesomeric effect. It is also, this is something I have given you the example of nucleophilic reaction. Similarly, the same effect can be also used as directive influence. Directive influence in electrophilic substitution of benzene. So these groups are having electrophilic substitution reaction, directive influence in that. For example, these are auto and para reacting. These are meta directing. The new group will be directed towards ortho and para position by these groups, while this group will be directing the electrophile at meta position. This will be taken up next time. That's all for today. Thank you very much. If you are having any problem, so you can again, I have already told you, you can give me ring and bring forward your problems. What is the number? Number is this. So you can contact me at this number and send me your problem so that we can make the things as per your requirement. Otherwise things are that simple that one can do it oneself also. But still, if you are having anything to ask from me, so that will be, I will be always appreciate that. 9463477804. So you can bring your problems and get it solved. Thank you very much.